The GRASP Laboratory at the University of Pennsylvania is planning to field a team for the upcoming MAGIC 2010 competition. This competition will provide unique challenges across many aspects of robotics, including sensing, mapping, planning, coordination, control, and human-machine interaction. Fortunately, the GRASP Laboratory has a long history of dealing with such challenges. The Multiple Autonomous Robots, or MARS project, sought to develop a framework for the deployment of many autonomous robots in an unstructured and unknown environment. Applications range from reconnaissance and surveillance to the removal of explosive ordnance. Rather than rely on human supervision of robotic agents, the objective was to develop the software framework and tools for a new generation of autonomous robots. In this sequence, an autonomous ground vehicle developed at GRASP is navigating an indoor, obstacle-rich environment using an omnidirectional image as its primary localization sensor. The main components of the MARS project were demonstrated in 2001. These included the methodology and the software to enable robots to exhibit deliberative and reactive behaviors in autonomous operations, to be reprogrammed by a human operator at runtime, to learn and adapt to unstructured dynamic environments, and finally to provide performance guarantees for their missions. The Mars 2020 project featured researchers from the University of Pennsylvania GRASP Lab, Georgia Tech, the University of Southern California, and BBN. The project goal was to develop the enabling technologies to permit heterogeneous groups of autonomous mobile robots to operate as a team with minimal human oversight. To demonstrate this, we chose a surveillance mission. The 2004 demonstration featured 4 distinct types of ground robots and an autonomous air vehicle. These in turn used 3 different types of system software at the platform level, but were coordinated at the team level by a common mission plan and operator control system. This approach permitted interactive interrogation and even reassignment of any of the robots at the task or team level rather than the individual platform level. The scenario began when the target of interest, identified simply by an orange vest, entered the area. A surveying UAV was tasked with searching for targets of the specified color. When a candidate target was detected, a text alert message was automatically sent to the human operator, who could then request imagery. Autonomous ground vehicles were then launched to explore the vicinity and verify the image content. Some vehicles acted only as radio network relays for the others with more flexible surveillance sensors. Full network connectivity was critical for the team so that any vehicle detecting the target could immediately send an alert to the operator. To maintain connectivity, the vehicles used real-time and mapped radio link state data to tailor their motion commands to maintain or re-establish network links as required. When the target of interest reappeared, it was detected by one of the robots. An alert was automatically propagated through the network. The use of text alerts allowed the operator to selectively request images, so the communications network was never flooded. Other robots also received the alert. They in turn responded by moving towards the area of detection, storing images, and triggering further alerts as they detected the target. The DARPA Urban Challenge project was started in 2006 to develop an autonomous robotic vehicle capable of driving in dynamic urban environments. The overall objective of the project was to build an autonomous vehicle capable of passing the California driver's license test. Applications of such a system include the potential for unmanned convoys in unsafe urban settings, as well as enabling driving mobility for handicapped people. The vehicle platform consisted of a commercial Toyota Prius gas-electric hybrid automobile modified to enable drive-by-wire operation. A sensor mount rack on the top, hood, and sides of the car provided inputs to the perceptual system. These sensors consisted of 2D and 3D LiDARs, as well as a color stereo camera system. A set of 6 Mac Mini computers in the trunk provided the computational infrastructure to process the sensory information, map both static and dynamic obstacles, and then plan optimal trajectories according to the map and high-level goals. This sequence shows how our mapping fuses information from the LiDARs and cameras in real time. The surrounding terrain was classified probabilistically in terms of drivability, with blue being very traversable and red indicating bad regions. A trajectory that optimally minimizes a traversability cost is then generated by the planner, respecting the non-holonomic constraints of the vehicle. This information was then used by the low-level trajectory controller to actuate the steering, throttle, and brakes to follow the desired trajectory at speeds up to 25 miles per hour. This next sequence shows how the perceptual mapping and planning modules interacted with high-level mission goals and constraints to safely navigate a crowded intersection. As our vehicle approached a 4-way intersection, it first waited to see whether another robot would traverse it. That robot had been disabled, so after waiting the requisite 15 seconds, our robot made a high-level decision to proceed out of turn through the intersection. However, in the meantime, another robot had illegally attempted to pass the stuck robot, and in turn got stuck in the opposing lane. As our robot made a right-hand turn through the intersection, it encountered this robot headed in the wrong direction. As the other human drivers started to panic in this situation, our robot waited until there was enough clearance to safely pass these stuck robots. After doing so, it navigated back into its lane and successfully continued with the rest of the mission. This sequence displays the response of a very adaptive system obeying high-level constraints specified by humans, but autonomously sensing and navigating a difficult, dynamic environment. The experience gained in this challenge will be critical for the success in the MAGIC 2010 competition. The following sequence shows an example of some recent work done in conjunction with the CTA MAST effort. Here we consider the problem of controlling multiple aerial robots to manipulate and transport a payload in 3 dimensions via cables. A team of quadrotor robots is tasked with the coordinated lifting of a triangular payload. An individual quadrotor UAV is unable to lift the weight on its own, so the team must coordinate their motions to apply the proper forces at the right time. In order to accomplish this task, a cooperative controller is used to guarantee conditions for static equilibrium and maintain a valid system configuration of the aerial team at all times. We have seen some of the GRASP laboratory projects that are closely aligned with the goals of the MAGIC 2010 challenge. In addition to these, the GRASP Lab is conducting a number of other ongoing research projects. These projects span the gamut from learning controllers for legged locomotion to planning with uncertainty in high-dimensional spaces. The laboratory is also working on other projects that focus on legged locomotion, robotic manipulation in collaboration with Willow Garage, and modular systems. If you would like to learn more about these and other projects, please visit our website at www.grasp.upenn.edu. In conclusion, we have seen that the GRASP Laboratory has recently developed and is currently doing research on many of the key enabling technologies needed to successfully complete the upcoming MAGIC 2010 competition. With the team of researchers and students that we have assembled, we look forward to solving the key challenges that lay ahead. Thank you.